Okay, I say it's, I don't know how many years ago. I got an opportunity to spend 2 summers at NASA's Langley Research Center. I remember, and one of the projects that came out of that was, this is retired now, our space shuttle, but the fuel on the rocket itself was liquid hydrogen and liquid, does anybody know? Well, I just wrote it. Oxygen. To make water, and boom. Right? Oh, just big explosion. So it's rocket fuel. So hydrogen is very explosive, and the problem is that they have they still, well, don't have a rocket anymore, but I guess it's still useful. Detect hydrogen, right? If you probably shouldn't be smoking, right? But if you are a smoker, you light up and the darn thing blows up if you have a hydrogen leak. I think the real concern is these electric cars are the big thing now. Fuel cells is really the technical word for it. And we've got a lot of water on this planet. So you break up water, you get hydrogen and oxygen. Use the hydrogen to generate electricity. That's pretty much what a fuel cell's doing. The problem is okay, you fill up your tank with water, right? And the technology's not there, but this is the idea. Fill up your tank with water, right? Generate some hydrogen. Where does the hydrogen go? Well, it probably goes to some big container or something. What if it has a leak, right? And let's pick on Caroline. Come up here, Caroline. Caroline is a smoker. And a car that, come on up here. And a car that runs on hydrogen, hydro bus, right? So she's got her hydro bus, and she lights up her cigarette, and the hydrogen ignites, and, right? If you don't like loud sounds, you might want to cover your ears. Oof, right? Thank you, Caroline. So you don't want that to happen, so you want a little sensor to go off. NASA's got a sensor, but it's electrically based. With any electric circuit, you can have a short circuit, and then boom, right? Okay, so one of the projects that came out of that was, okay, NASA needed a fiber optic based sensor, right? Fiber optic, it's glass. So you can have that little glass line running anywhere. Outside, the space shuttle, extreme environments, space, wherever, it would work great. And have a little pad or even coat the fiber optic itself with something that would change color in the presence of hydrogen. So that's what this guy is. And there's a catalyst in there. That's why I brought him. And the catalyst is platinum, but everything else in there, can't tell you. To kill you, right, Maria? It doesn't. It's got some problems, and you're going to see. It may not even work today. So the thing is it should change color in the presence of hydrogen. So what color does it look right now? It looks kind of green, grayish, right? Okay. Hydrogen is heavier or lighter than air? The balloon is a hint. Hydrogen is lighter, right? So I got to transfer it, unscrew this guy, and then flip the guy around here. Maybe it'll work, maybe it won't. Ooh, it did. All right? See what color that guy is? It's not green anymore. It's kind of black, dark bluish, right? It worked this time. Didn't work at 111. I didn't heat the crud out of it. If you saw me, I was heating the crud out of it. In the technical jargon of the sensor world, that's called regenerating. So that's not, come on. Some dude's going to have to climb out on the end of the space shuttle and have a torch and to regenerate the sensor? That doesn't make a whole lot of sense. The other problem with this sensor is, the reason why, again, why I'm still here and not a millionaire, is this guy, hydrogen is explosive at a much lower concentration than this thing will change color. So Caroline goes into her little hydro bus, right? The little green sensor is still green. Oh, I can light up. Because the sensor's not sensitive enough, right? So, but, it makes a good demonstration. So the catalyst is platinum, but what does the catalyst do? and it's exothermic. The guy's kind of hot, or you'd have to touch it to believe it. But all a catalyst does is lower the hump. Catalysts can't change the energy of reactants or products. All it can do is just lower the hump. In fact, the technical jargon is what, Jasmine? It lowers the activation energy. Excellent. It lowers the activation energy. And we'll have a problem on that by the time you leave class. We'll actually have to draw it. Okay, so we're supposed to talk about elementary reactions and catalysis. We kind of covered the catalysis part. Elementary reactions. What is the difference between, Jessica, an elementary reaction and a reaction mechanism? An elementary reaction, reaction mechanism. What are they? Anybody have a clue? An idea?
This one that goes one way, or it's a reaction that goes.
Yeah, they kind of do just go one way. These elementary reactions. The thinking is usually we're so used to writing reactions, right? This is all of our what? Reactants. And then we have all of our products over here. And we've never really cared how the reactants actually got converted into products. But if you're synthesizing some drug or some compound that's worth several $1,000s an ounce, you want to make a lot of the stuff, and you want to make it fast and really highly efficiently. It'd be great for you to know exactly how that thing is formed. Every single little step along the way. It may be more complicated than just adding the stuff up and making products. It may occur in several steps. That's what a reaction mechanism is. Big money in that. If you can figure out what the reaction mechanism is for, I don't know, breast cancer. What the heck is, where does it start? What's the intermediate steps? What's the key step? Maybe if we can just mess up this one step, we can stop it all from happening, right? Just an example. But the point is to get the overall reaction, just add up all the individual steps, right? But each individual step is a reaction. Well, they're all everything's a reaction, but the point is each individual step is an actual collision has to be going on. That molecule A has to physically collide with molecule B and make molecule C. And then molecule C has to turn around and collide with A to make D. And that's the overall mechanism. So you can't even get this reaction to progress unless you make some C in the first place. So if you could stop that from happening, you'd be great. Even though, well, what is the overall reaction? Does C even show up in the overall reaction? Right? Yeah, it doesn't. What's the overall reaction? Add up all the reactants? Add up all the products? What are the overall reactants in this overall reaction here? Mari, what would you write? 2A plus B. Exactly. Right? C's canceled out. And then the product is just D. So that's the power of a reaction mechanism, is that you discover these reaction intermediates that really inform you what the heck is going on. Okay? So overall reaction. These are called what type of reaction? Elementary is the word we're supposed to use. Elementary. So a mechanism is just a whole bunch of elementary reactions. This molecule collides with this one and makes this, and then this collides with this to make this, and actual molecules colliding. That's not the case for an overall reaction. Very different, right? Okay, so what's really coming up, the big picture of all this, that were mechanisms and things, is that we've been trying to figure out how to write rate laws for this guy. And we had to do all these experiments and figure out the exponents and things. Today, you're going to like today. Today, we're going to write rate laws for individual elementary reactions. It's going to be nice. You'll like it. Guaranteed. Okay, some more terminology, though, before we get to that. Molecularity. You have an elementary reaction. What is its molecularity? Okay. Oh, let's just pick one. Well, you have step 1. It has a molecularity. You have step 2. It has a molecularity. What's the molecularity? Vanessa, what do you think that is? Number of molecules on the reactant side. Exactly. So for step 1, the molecularity, Monica, is 2. Everybody, for step 2, the molecularity is 2. Yeah. It's just the number of reactants involved in that elementary step. Okay. There's 2 reactants in each of those, so it's just 2. Okay. Right here it is. Writing rate equations for elementary reactions. Just how fast are these individual little steps occurring? Okay. And you can write a rate law for them. And we'll do it just as before. Rate equals, and then Brandy, what are you supposed to write next? Supposed to write what symbol? K. Okay. Now here's the trick. Before I said, don't do this. Don't put a, right? Remember that? Don't do that, don't do that. But now, do that, do that, do that. Because it's an elementary reaction. A has to collide with A. So it's very straightforward to write the rate laws. You don't do experiments. You just have to have been told that it's an elementary reaction. That's the only time you can do this, is they tell you it's an elementary reaction. Then just go ahead and write it. Well, if that's the case, Brandy number 2, how would you write the rate law for the next one? Yeah, keep going. Yeah. And you can write the little ones or superscripts if you want, but it's not necessary. Okay. Okay. You're given a mechanism. Okay. And then they say one of the steps is a little bit slower than the other. And then they want you to write the rate law for the entire mechanism. They're not giving you any experiments or anything. They're just telling you, ooh, one of the reactions is slow. What do you think the rate law would be for that mechanism? Because now you, right? Think you have an expression to write the rate law for each step, because they're elementary reactions. If you go through the work and find out that one of those steps is extremely slow, which one would determine the rate of the entire thing? The slow one. Think about you're going to Austin, right? You're going to Austin. And where does the traffic really get bad? Like 281 kind of area, right? Okay, they're doing construction. Imagine they're doing construction on 281. Now it's down to 1 lane. It's even worse, right? The time it takes you to get to Austin is completely dependent on the time it takes you to get through that little bloody section of 281. It's a bottleneck. Nothing can progress until you get through that bottleneck. Doesn't matter where the bottleneck is. It can be at the beginning of your trip or the end of your trip. Same thing with the mechanism. Doesn't matter whether it's the first step, second step, the middle step, the last step. It doesn't matter. It's the bottleneck. It determines everything because it is so slow in comparison to everything else. You go into Austin, you can drive 65, 80, whatever, until you hit the bottleneck. Then you're out of luck, right? Once you get through it, now you're back to 80 again. So nothing else matters. It's only that bottleneck. So how would you write the rate law if they tell you the slowest step in the mechanism? How would you write the rate law for the mechanism? Just write the rate law for the slowest step. They call it the rate determining step, RDS, the rate determining step. But this is their notation. They're just going to tell you which one's really slow. So how would you write the rate law then for that mechanism summer?
Rate equals K, and
Yeah, and B. Done. Nice, huh? Okay. Let's see if Eric can make sense of this. Eric, I don't know if you believed me or not, but I had my little hydrogen sensor, right? And I told you that platinum was the catalyst. Technically, would that platinum be a heterogeneous or homogeneous catalyst? He's right. All right? Good guess, right? Hetero, because it is the platinum. Now, the platinum is a solid, liquid, or gas? Solid. And what's the little reactant that we're trying to detect? Boom. We're trying to detect hydrogen, and it's a gas. They're different states. Therefore, platinum is a what catalyst? Heterogeneous. It's just the state. If the catalyst is in the same state as the reactant, exactly what he said, then if it's the same state, it's homogeneous. Different states, heterogeneous. So platinum would be a heterogeneous catalyst in the hydrogen sensor. Okay. So I say we make life a little bit interesting, get you off your can, go to the boards, knock these out because they're all conceptual, and then we can call it a day. So just write down your answers. You don't need to write down the question. Just write down your answers. What is the molecularity of each of the following reactions? So just write down what you think is the molecularity of each of these. You're just on the spot. Or if you want to, you can work with Caroline in the back. Look at all that space. All right here, right where you're at, yeah. All right, so we're nice and spread out. There's a spot right there. You have your own personal board.
Are you going to go up here?
Okay, so write what you think is the molecularity for reactions A, B, C, and D. You don't need to write down the whole reaction. Just write down what you think is the molecularity. See if it agrees with what the folks around you are writing. Can't see what you wrote, Summer. Oh, Brandy, it's just the reactants. 1, 2, 3. All right. Does everyone pretty much agree? That's all one molecule.
Okay.
Yep. Okay, so it looks like for the first one, everybody answered. For A, everybody put 3. For B, 2. This whole guy's one molecule. For C, 2, and last one, D, 1. Yeah. All right. Write a rate equation for each, or showing, they make it sound complicated, showing the dependence of rate on reactant concentrations, but there's just 2 words up there that are key: elementary reactions. They're telling you that these are elementary reactions. So then writing the rate law is pretty straightforward. You can jump in here. Or next to Mari, look at all that space. Oh, don't forget your little 2. It's carbon disulfide. Yeah. think everyone's got the same thing. Right? I think everyone agrees. Okay. We're good? Let's check out. Okay. Now we're getting into something here. Let you read it. See how confused I can get you? Okay. A lot of stuff in there. You're supposed to answer. They're going to tell you something that happened, right? And then you're supposed to answer, does the rate increase, decrease, or remain the same? And then say why, right? Okay. So they're dumping in some sodium hydroxide, right? You see the game on how to do any of these? But do you have a game plan? There's one thing you could do, is see if whatever they say shows up. Shows up in what? Products? Reactants? Shows up in the rate law. So I'm going to try to boil this down so that it's not near as complicated. There's so much blah, 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 blah. All you care about is this. It really doesn't matter what else they say, because they want to know the effect on the rate. You know everything that affects the rate. It's in the rate equation. Everything is there. So who cares about anything else they say? Just block it all out. You just care about the rate equation. Okay, now let's take a closer look at the rate equation. Something in that rate equation is written in an oddball way that I never write it because it's too much work. It's the what? Oh, I guess I wouldn't write that S in parentheses. That's a good point. I wouldn't do that. But something else. Yeah, there you go. What is the H3O plus? I never, ever, ever, ever write that. You never, ever, ever write that. We always write what instead?
H2O.
Not H2O.
H plus.
H plus. H plus. Now Monica was saying how you get the H3O plus. You add
H plus H2O.
H plus H2O. That's how you get it in the first place. H plus H2O makes H3O plus, and we even had a name for it. Third than H. Someone remember? This is how they think H plus exists in water. That's the only reason why we talked about it, because technically bare protons don't exist in water. They think H3O plus mostly does. It's called hydronium. It's called hydronium. But we never used it because whether you use H plus or H3O plus, you get the same answers for everything. Technically, you should write H3O plus all the time. But then you're always going to have to write H2O on it, to generate it. So it's just easier just to leave it alone. Okay. Does that help answer this first question? Still doesn't. Okay. So let's take a closer look. When you have compounds, right? I told you not to look at certain ions because they never do anything. Do you remember which ones they were? Yeah, with these salts, right? Yeah, kind of. those group ones. This goes back way back when we had a list of all these different reactions, and we had to recognize, oh, an acid plus H2S gave, all these different things. I don't know if you remember that, but the point is here you're supposed to see NaOH. You're supposed to see that as OH minus. H plus and OH minus will react and form what? H2O. What type of reaction was that? H plus is a acid. OH minus is a base. That's an acid-base reaction. So if we add NaOH, we are effectively doing what to this number right here? Are we increasing that number or are we decreasing that number? We're decreasing it because it's reacting up. Add some more OH minus. The rate's going to go down even more because you're removing something in that rate law. It needs it. Right? If you want the rate to go faster, make the solution more acidic. Right? So what's going to happen to the rate? It's going to decrease. And explain why. Put it in your words, why. It'll decrease because blah, 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 blah. You don't get it? Okay. The OH minus removes the H plus. So if it makes that, because really what the rate is just going to be a number, right? And you get that number by multiplying this number times that number times this number. They're all just numbers. And the H3O plus, this number we're making smaller. Well, that's not the H3O plus. This one is. We're making that one smaller because it's reacting with the hydroxide to make water. So its concentration is getting smaller and smaller and smaller the more that it reacts. So if that's getting smaller and smaller and smaller, well then this has to get smaller and smaller and smaller because the other two stay the same. Okay, so that's the game plan. See if you can answer B, C, D, and I added E. See if you can answer B, C, D, and E. Now you have to explain why too if you have an answer. See if you can figure out what's going on with B, C, D, or E. Okay. Maria, we just need the reason why in all these, if that's what you think.
Do I just write this? You know how it says it there?
Oh, so for the catalyst, yeah.
So
Catalyst will definitely increase the rate. Yep. Okay. Is anybody pretty confident on any of these? I think Jasmine's got a good answer for D, right? For D, it's carried out at a lower temperature, so things are colder, they're moving slower. That kind of makes sense that the rate would go down, right? However, a better answer than saying moving slower would be which thing in the rate is getting smaller. Right? In that rate equation, it's not the it's the K. It's the K. The K is actually smaller. So when you specify a reaction, you really got to specify the temperature, because you're going to have a different rate constant every time if you change the temperature. So that's a good one. Anybody see an answer to anything else? B would be increase. Anybody else have increase for B? Why? Well, we're adding H2O though, not H3O plus. It's like 1,000th of a billionth. If you take water, H2O, 1,000th of a billionth of what you added is H plus. So you're adding very, very, very little of H plus. What does water do? It's going to do what to these concentrations? It's going to that's the word. It's going to dilute them. It's going to dilute both of these, so the rate's going to go down. You just made things less concentrated. You're going to dilute. So H3O plus and what's the other dude? That's CH3CSNH2. Go down. Okay, we have two left. What's that? Which one? C. The catalyst rate goes up because, yeah, exactly, increase. K gets bigger. We'll see why in the next question. We only have one left after this. And we have one left. We're adding HNO3. Adding H. I added that one. I added E. The rate will HNO3 is a acid because it's got an H out front. So the rate's going to go up because I'm increasing the number of H pluses. H plus, it's really H3O plus, but they're the same thing. So the rate will increase because we're increasing hydronium ion. Because H plus and H3O plus are the same thing. So if you add an acid, you're increasing H plus or H3O plus, same thing. Last question.
So
Yes.
the answer is
The rate should increase.
no. It answers C because it's
In C, the rate increases because K gets bigger.
Yeah, but you
Bigger
said
rate
that
constant.
If we answer E, we'll know why C. Why K is bigger.
No, I must have misspoke or something.
But it's, why is it? Because
Oh.
catalyst adds heat.
Oh, a catalyst. Yeah. Okay. Good question. Why does C work? C works because of this question right here.
Yeah, that's right.
All right. Let's try this one. Then we're done. We need to draw a potential energy diagram. Okay, and remember how to do that, where you had to label the energy of activation and you had to label delta H, reactants and products, label the coordinates, right? So draw a potential energy diagram for an uncatalyzed exothermic reaction. Then in the same diagram, indicate the change that results on the addition of a catalyst. Okay? So see if you can do this. I kind of gave you a microsecond of a hint at the beginning of class. Remember what the x-axis was called? Reaction coordinate. Coordination or coordinate, yep. Okay, and remember it's exothermic. Good, so a lot of folks have, yeah, good. Reactants up here, products down there. Okay, the big picture is what? Okay, I have to draw a hump. Well, before I draw the rest of this, you can draw the delta H right now, because it's always a difference between reactants and products, their energies. So I can put that in right now. Right, wherever the products were at there, that's my delta H. Okay, so let's draw one of these in. Let's say this is the uncatalyzed one. Got this nice big hump, goes down. All right. Let's say that's uncatalyzed. And we can change a color. Catalyzed. Okay. So that's, they'll both have humps, but if I want to draw the uncatalyzed, how does it change? Hump gets smaller. That's it. That's the only thing you do. Now we should probably finish this. For my I didn't draw in my energy of activation, right? Isn't this my energy of activation? It's the energy that the reactants have to overcome to turn into products. So now I have to draw the catalyzed reaction, potential energy diagram. Just draw a smaller hump. But they both have to end up in the same place, right? Okay. And now my energy of activation is only right here is all. The only difference is the energy of activation is smaller. The delta H is the same. That didn't change. Okay. So that's how K got bigger. It lowered the energy of activation. So that's about it. So lab tomorrow. If you have some questions or you didn't do so hot on the quiz for today, man, come by tomorrow in lab. Be glad to help you out. If you have lab tomorrow, just ask in lab.